just happened? Oh, no. Oh, hey, we're back. Okay, sorry about that. A little false alarm there. Okay, so this video is going to be about confidence intervals. And so the idea here is several fold. You can come at these from a couple different points of view. So I guess the first one we'll talk about is suppose I don't know mu. I don't know the population average. Now you're like, Jay, I never know mu. Well, okay, that's true. That's absolutely true. I don't know mu, and I really have no clue. In other words, I might know what it's supposed to be, but I really have no clue. I really have no clue what it really is. And other times I might not know at all. Like, for instance, what's the average age of, I don't know, first time someone's diagnosed with, I don't know, some sort of disease. Okay? I don't know. In other words, is it the average age closer to 30 or closer to 50? Why would that matter? Well, knowing when they can go in and get their routine exam, whether it's a breast exam or a colonoscopy or whatever it happens to be. Colonoscopies, they recommend, I think, 50 is the first time now, because it's not a young person's game, right? It's not something a young person gets, generally speaking. So when you're 50, go in and get your first one, okay? How'd they know that? Well, they've collected data over the years, but it's a situation kind of like I'm talking about. I don't know what the average age is, so you go out and take a sample, okay? Now, that's one way to do it. Another way is I know what it's supposed to be. But is it still that? And this would be a situation where you're on an assembly line or something, okay? You're supposed to be making a doodad that has an average height or weight or whatever of this and such. It's what it's supposed to be. Is it still doing that? This would be a quality control situation, something you do every couple hours, every hour, whatever, make sure the machine's still working properly so that you can, shut it down if it isn't. Okay? It's really an easy process, honestly. Once you understand it, it's just like, oh, sweet. Now, the good news is this is the first time I've ever done this way. Last week we talked about hypothesis testing first. So this is very similar to a two-tailed test. It's very similar. There's a little slight bit of difference here, though. Okay. We assumed what mu was on the last one, and so we found a probability of what we saw. Okay. Based on our assumption. But today we're not going to do that. Today, instead, no. What we're going to do today is say something like this. We are going to put, say, 95%. That's our most common one. We can put anything in here if you wanted to. We're going to build what we call a 95% confidence interval for the true mean. Okay? And how are you going to play that off? Well, here's the game. You're like, wait, 95%. That means 2.5 on the outside. That's right. Wait, that means this is 1.96 and this is negative 1.96. That's right. Wait. So what you're saying is I need to pin my z-score between these two values. That's right. But wait, I know everybody but mu. Yep. And if you play a little algebra, I'm going to multiply both sides by this guy. Well, actually, not both sides, all three sides by that guy. And by the way, you'll never have to do this part again. Once we get down to the final answer, you'll see what I mean. This is just where this final answer comes from. Sometimes it kind of annoys people. They cannot see how I got from one to the other. I'm going to minus x bar to all three sides. And I don't want negative mu. So I multiply everybody by -1, which flips the signs, which means this is going to now be the smallest side. So I'm going to stick it on the other side. So it's going to become positive x bar minus 1.96. And in reality, so that's a 95% confidence interval. In reality, you can put any z right here you want. So, for instance, if you wanted 90%, that'd be 1.65. Okay. And you could continue on. I could make it a 50% confidence interval, Jay. Well, that's ridiculous, sir. The idea of confidence interval is you want to be, wait for it, confident. There you go. Now, there's always a happy medium, friends. Always a happy medium. Okay? Keep this in mind. Like if I tell you, if someone comes up to me and says, "Hey, I'm a great shot," I'm like, "Oh yeah, yeah, I can hit the target 95% of the time." Dang, boy, nice shooting. Yeah, yeah. How big's the target? Well, that barn over there, that giant barn. Correct. It's this ancient barn. It's falling down. Wait, what? Yeah, you can hit that thing from. Okay, well, like from how far away? Inside it. Whoa, dude, you can hit it 95% of the time when you're inside of it. That's pretty sad. Okay. But if the target is like, oh, well, I can hit a dinner plate. Well, okay. How far back? From 5 yards, I can hit that thing 95% of the time. It's kind of sad, bro. It's kind of sad. But if you're hitting a dinner plate at 300 yards, that's good shooting, boy. It's good shooting. With a rifle, let's say you're pistol, obviously, that's just ridiculous. But let's move it out further, right? And then you're like, oh, cool, yeah. If you, by the way, if you hit a plate 20% of the time, or 15% of the time, or 50% of the time, I wouldn't be bragging about that, right? So there's that idea that the further you get away, like we're shooting targets here. The further you get away from the target, obviously your percentage is going to go down, obviously. And then the bigger the target gets, the percentage is going to go up. At some point, you can make the target as big as you wanted to. Like you could say, like, I'm going to want to be 99.99999% confident. Well, here's the problem. When you do that, okay, what does that do to the 1.96? Well, in effect, what you're saying is this. You're moving them out here in the tails further. Maybe you get a 5 here for a z-score. Something like that. Something ridiculous, right? Well, wait a minute. That would mean that I'm out like 7 miles wide. That's right. Well, that'd be like saying that I am 99.99999% confident that the average height of an American woman is somewhere between 4 foot and 7 foot. Well, Jay, that's not very confident. No, that is not very confident. You are correct, sir. And so the problem is you get out too far, the target is so wide, it doesn't mean anything. Okay? So 95 is our sweet spot, is our happy spot. That's where we use most of the time. And so you'll see this 1.96 pop up because of that. Again, if it was 90%, 1.645 is what we always used back in the day. When I was a kid, that's the one we always memorized. But whatever. And you could go crazy from there. Those are the two we normally use. 2.57 is 99%. I've never ever done that outside of a math classroom. So I will not be asking you that. Now, we'll take this one step further, and we typically will write this as x bar plus or minus. And I'm going to write it as z, but you could also put the 1.96. I'll leave it as just a generic z for right now. This piece right here is called the margin of error. Okay, it's called the margin of error. So we'll say something like this. We are 95% confident. The true mean is somewhere between 50 plus or minus, let's say 53. If this was my margin of error, that means somewhere between 53 and 47. I apologize. My allergies are fired up this morning. Are between 47 and 53. Okay. And that's where we leave it. Now, you're okay to leave it like this. I like this a little better, maybe. Okay. We can also say that it's on the interval from 47 to 53. You can also write like that. Okay. Now, depending on what you're talking about, we either go ahead and add that margin of error or we don't. So if this was somebody's popularity, 50% of the population likes so and so with a margin of error plus or minus 3 percentage points. When we're talking about polling data and percentages, which we're not going to get into, but if we're talking about that, we typically leave the margin of error not added on. Okay, it's just a different preference. It's kind of the same way when, I don't know, you can talk about probability and stuff, but typically my rain forecast is a percentage. And typically my odds, when you give someone odds of winning or probability of winning, you give them, a lot of times you'll give them a fraction instead. It's all the same, bud. It's all the same. Okay, so another question then, of course, is how do I go about doing this? All right, well, you want to know something about the average average length, average number of ants per ant hill. Oh, brother, I got to count all those little devils and I'm going to get stung. Yep, probably. Have fun. So you sample. Sample. That's what we always do, baby. 100 hills and find the average is, I don't know, just made that up, with standard deviation of 419. Sure. Cool. And then, so we want a 95% confidence interval for you. So it's really this easy. You need 3156 plus or minus z, which is 1.96, times 419 over the square root of 100. That's it. It's very formulaic, man. So 3156 plus or minus. Now this is, check it out, this is 10 on the bottom. 419 divided by 10 is basically 42. It's 41.9, obviously. And then we're taking basically 2 times that. Okay? So we're going to end up with like 83-ish or something. I'll do the math on my calculator. 82-ish. I'm just going to call it 82. Okay? Remember, that's technically not wrong. We're going to go ahead and add it up. So if I add 82, I get 3238 on the top end. And on the bottom end, I get 3074. That's it, man. I wish I could make it harder, but that's all there is to it. Now, again, we are going to do several here in examples-wise. I'm not trying to hurry through it or anything, but I'm saying that's legitimately all these things do. Now, when we're doing them, okay, and we're thinking to ourselves, oh, okay. What do I want to say with that? So, what do I do with that? Okay, well, again, you didn't know. So you're an entomologist, you work with these little devils, you'd like to know how many little buggers I need, etc., whatever. You can be 95% confident that the next, if you will, it's not exactly this, but we treat it like this. That it's 95% of all ant hills, you can think of it, will have somewhere between those two, in theory. Okay, now that's not 100% accurate. Now you think about why that is. Okay, the reason that that's not 100% accurate is because what did we do? We took a sample of size 100. Okay, now sample size 100, what happens to these guys? This gets smaller because that 100, well, I mean, versus, let's say, a sample of 50 versus a sample of 10, because, of course, this denominator is getting bigger. What we found was that if you took a sample of size 100 different anthills, 95% of those samples would fall between those two values. Okay? 95% of those guys would fall between there and there. Okay? Give me an example, Jay. Oh, here's an example. Suppose you were to go and you've seen me generate some data on Excel, and I probably will do another set here in a second. If I were to do that, and I were to go out and I would find, let's say there's 100 anthills, 100 anthills, and I add them up, cool. And there's another 100 anthills, and I sub those up, and so on and so on and so on, all the way across. Okay, and then I take those guys. That would be one sample of size 100. Cool. And then I did it again and again and again and again and again. Cool. Awesome. Well, 95% of those samples would fall between there and there. Now you're like, well, how does that help me as a general entomologist? Generally speaking, well, the way we talk about this is this. We generally talk about this as saying, hey, there's about 95%. It gives us an idea, a range, where we're very confident the true average is between here and here. Okay? Now think about why this wouldn't work for the average anthill. The average anthill may very well have this exact same, it'll have this exact same mean or something awfully close to it. That's 100% true. Just one single anthill. But remember, if it's a single anthill, then we're still doing this 95% thing, but this single anthill is 419. Okay? So single anthills are going to be a lot more variable than a sample of size 100 of them because of the central limit theorem, right? So what we're saying is this. We are not talking about the average. We're not talking about the average. We're not talking about for each individual ant hill. What we're saying is this. We are 95% confident that the true mean is between here and here because we took a sample of size 100. Okay? Now, that's something to think about. All right? In other words, if you go out and sample one anthill right now, and let's say it's on the edge of kind of a desert, and you're like, gee, I only got like 2,700 or something of them. Is that weird? No, it's not weird because it's a single one. Okay? It's going to be an outlier, obviously. Okay? But if you went and took a whole bunch of them, obviously, the samples, oh, what? Because you took a sample size, a bigger size, 100 or 50 or 10,000 or however many you want. It doesn't really affect anything. We're talking about the average. This guy right here is going to be awfully close. And we're going to be able to pin it down because of the fact we took a bigger sample size. Now, note what happens if you take a smaller sample size. What if n was only 50? What happens to our confidence interval this time? Well, it becomes 1.96 times becomes 116. Now, look what I am. I'm still 95% confident, but now my target is quite a bit wider. Why is it wider? Because I had to make a bigger target because I was to be just as confident. Because why? Because my standard deviation is so much bigger now. My standard deviation is bigger than this guy now, right? So my standard deviation was, let me write that down, hang on. So let's do that. So instead of being 441.9 like it was on the last problem, it's 59 this time. Because this is so much bigger, that's going to make then my confidence interval that much bigger. Okay? In other words, I have to go out quite a bit further to be just as accurate. Okay? That will always be true. In any confidence interval situation, right? The bigger the sample size, the smaller the confidence interval. It'll always be true. Now, at some point, you run into diminishing returns, right? Well, bigger is always better. Well, no, that's not always accurate. On some things it is, of course, but at some point you're like, well, geez, 100 and 1,000, for all intents and purposes, might be almost the same in terms of, it doesn't really help me at all. So then why would I do the bigger one? I wouldn't, okay? Or like you're working in a factory. Listen, I need a good, quick, are we still within spec? Well, if we're still within spec, let's keep rolling. I don't want you taking all my product off and damaging it or not letting me ship it while you're fooling around with it. I can't have you doing that. I can have you take off 30 or 40 at a time. That'd be fine. I can't have you taking 1,000 at a time off. Hey, where's the product? Well, we're testing literally every piece. That's not helpful. Not helpful. Okay. So let's do another here. So again, here you are at the assembly line. You get little packages coming by. Nice, whatever. Bloop. Into the bin down here. Okay, you work, I don't know, maybe it's Santa's workshop. Yes, good. Santa sure is making, I don't know, Jack in the Boxes. That are supposed to be that are supposed to jump out. That are supposed to jump out 10 inches on average. Clyde, the elf in charge, EIC, of quality control, tests 30 every hour. 1 hour, he finds the average to be 10.17 inches with standard deviation. Nice. Let's find the 95% confidence interval for that. So again, it would be very straightforward. 10.17 plus or minus 0.96, 0.37 over the square root of 30. Hey, that was pretty quick. It is. It's really a straightforward process once you get the hang of it. It's just literally doing the same thing 100 times. That's fine. The question is, what do we do with it? Because this, again, it's a very important concept here, right? It's a very important concept. Oh, you idiot. Square root of, there you go, 30. 0.132. And so I would get somewhere between 10 point, oh, you moron, learn how to type. 10.3 on the top end, and on the bottom end I would get 10 basically 10.04. I'm just gonna call that. Anything weird about that? I'm 95% confident that the true spring height, whatever, is 10 point, so between 10.04 and 10.3. But I thought Santa wanted him to be 10 inches. He did. What does that say? Shut it down. Shut it down, baby. Why? There is a problem. It was supposed to be 10. It's not 10 anymore. Right? In other words, we're 95% confident. Hey, it ain't, it's between here and here. And guess what's not between there and there? 10 is not between there and there. Okay? Now, frequently you'll see this on a production line facility sort of a situation. Frequently you'll see that. And you'll see it done this way a lot of times. Other times they'll kind of come at it from a different point of view, which is similar but slightly different. So I'm going to show you both of them. Because I want you to feel comfortable with both of them. But again, shut it down. We did a test. We know what it's supposed to be. What it was supposed to be did not fall in our interval. Ooh, yeah, that's a problem. Now, had this come out to be like 9.6 to 10.2 or something, guess what? Roll with it, baby, because where's a 10? Well, our 10 is in here, hanging out with the unknown mean. So the unknown mean could very well be 10. Yay, keep the machine rolling, baby. Keep it going. Not so much here. Now, again, Santa could have done it a different way, and this is how it's frequently done in a lot of manufacturing plants. Because you hire some rando off the street, not really, but kind of, who doesn't have a background in statistics. And so instead of having them do that whole, I mean, not that this is hard. Not that this is hard, but they had to find this. I mean, granted, they used a calculator probably to find their computer. They still had to find this. Well, you get to multiply and divide by a square root. Oh, that's a lot of work. Oh, gee, it's too much work. So instead, what they'll do oftentimes is they'll assume they know what mu is. All right, just like we did with the two-tailed test. And so what they'll do instead is they will basically, this is a different way of doing this, but again, this is not a confidence interval. This is related to a confidence interval. Okay? A confidence interval always starts with X bar. But as I was saying is you will see something like this in manufacturing done a lot like this from time to time. And they will use what they assume this guy to be. Okay, they'll assume it is. They will have some idea what either what it's supposed to be, or they may have taken a sample and used some value of SX. Okay, but regardless, what they'll do is they will get something like this. Santa would have said, "Listen, if it's between here, oops, you idiot. If it's between here and here, let's keep rolling. And if it's not, let's shut her down." Well, what if what's between here and here? Well, if, again, this is 10 plus or minus 1.96, blah, blah, whatever this garbage is, okay? And anyways, it doesn't really matter what this part is. If, let's say it was 0.2, okay? If you take a sample this hour, and my sample comes out to be 10.1, keep it rolling, baby. If I take another sample next hour, and it comes out to be 9.81, keep it rolling, baby. Take a sample next hour, and I got 9.6. Shut it down, okay? It's the same premise. It's not the same thing, okay? So a lot of times in your manufacturing, oh, we're in a hurry. We got things to do. I can't bother to take my time to teach this fella, this person we hired here. I can't have them, and then I also can't I don't have time to teach them how to do statistics. Number one. Number two, I don't have time to go through the ins and outs of why this, that, and the other. And then I also don't have time to have them make stupid errors in calculations. Okay. If all they were doing is measuring, inputting it, boom, there's an average, and then compare the average to this interval, it's less likely to be able to screw that up. Not impossible, of course, because everything's possible when it comes to screwing things up, but it'd be a lot harder. Okay. So again, it's not the same thing, but once in a while, and every time I teach this, I have someone say to me, "Hey, that's how my boss told us to do it," and that's exactly right. Again, it's not the same; it's a very similar process. Okay. So then, let's see. I don't know. Got another one here real quick. Suppose you, I don't know, Kate, wants to know the average number of, I don't know, rose orders for a given week at her wholesale flower shop. I don't know. So I don't know what she does. I suppose she samples 50 weeks. She finds the X bar is equal to, oh geez, she's a big distributor of roses. Look at that. That's just ridiculous. That's too many roses. This is just the rose orders. I mean, some of these jokers are they're ordering 24 roses because they're idiots. I mean, they're idiots in terms of like they screwed up. So here, honey, here's 10,000 roses. Awesome. Well, that'll fix it. And of course, there is a bit of a standard deviation here. And awesome. So she samples 50 weeks. I can't even read what I wrote there. Weeks. Neither can we, Jay. Yes, I know. I saw you. And she wants a 95% confidence interval. Well, let's do it. So 13,900 plus or minus 1.96. 700 over the square root of 50. And again, I'd just like to point out the bigger n is, the smaller this value is. And the smaller this value is, the smaller your confidence interval is. Okay, and that's always true. Take it to the bank. Okay, let's get that margin of error. Again, if it's me, I find the margin of error first. The 1.96 times 700 divided by the square root of 50. And I get 194. So 13,900 plus 194 is 14,094 on the top end, and on the bottom end 13,706. And again, that's my 95% confidence interval. It's pretty straightforward. Not a very hard concept. Don't want to belabor the point. Now in class, of course, I'd have you doing some of these, playing along at him, etc. Okay. Now, I do want to show you one thing in Excel. Some years I teach it, some years I don't. I want you to see this so when you go out and you're working out in the field, you can perhaps utilize this if it makes you happy. I mean, if it's something that you can do, if your boss has you actually doing a little statistics, it's cool. So equals confidence dot norm. So what's my alpha? Now this is going to be careful here. My alpha is 0.05. So in other words, we have 95% in the middle. We've got 5% on the outside. Alpha is always the outside amount. Okay. My standard deviation was 700, Jay. Yes, in theory that's true. And then 50 for my sample size, and I get 194. Bam! What did it find? It didn't find the whole confidence interval. What it actually found was the margin of error. Okay, and you're welcome to use that on the test. I don't want you to see it done by hand, but I say you're welcome to use this when it comes to working out part of the project if you choose to go that route, and you're welcome to have at it and go to town that way. But again, it's something that we will do from time to time. Look at some of the Excel pieces. You need to understand what's going on with them. Now, here's a fun one. Suppose I want my confidence interval to be, well, how about suppose I want my margin of error to be $500. Okay? What I mean by that is this. I'm going to go out and take a sample. I'm going to create a confidence interval here in a minute. I would like this thing, it's not over 100, you dumbass, over n, sorry. I would like this whole thing here to be 500 in a minute. Okay? Now, what am I sampling about? I don't even know. I don't even know. Honestly, I don't even know. Okay? I haven't made it up. Car prices? How much money is financed? Sure, how much money is financed? It doesn't matter. I've decided that I would like this confidence interval to be 500. Okay? How am I going to get to be 500? The only way to do that is to increase the sample size or decrease the sample, change sample size. Right? That's the only way I can do it. This has no impact on it. So in terms of what the average is, don't care. That has nothing to do with my margin of error. Standard deviation is a standard deviation, babe. Nothing I can do about it. This is a 95% confidence interval, 1.96. Nothing I can do about that. Okay? So all I can change is my n. So in our situation here, what we're going to have is that the margin of error, which we're going to call E just for a good time, is equal to this guy. And the only way we can do these situations is to solve for n. And when I do that, it's going to end up being n, the square root of n, is equal to this. I'm just going to go ahead and, typically I'm going to write this over this way. And then I'm going to square both sides. And n needs to be at least this big. Okay? If n is exactly that big, obviously you'd be at 500 exactly dollars. And if you went bigger than this, if your n was bigger, then your margin of error would get smaller than 500. Okay? So let's give me an example here. So if I want the margin of error to be $500 on the amount borrowed for a car, I should say the average amount borrowed, right? And so I want a 95% confidence interval, and right now I get about 1,200. No, yeah, 1,200 for my standard deviation. Sure. So then what would n have to be? Well, 1.96 times 1,200 divided by 500. Yeah, I should have thought that through. Let's make this 4,000. Otherwise, it's going to be a very boring problem. So 4,000 divided by 500 is 8. Times 1.96 is about 15.68. Squared is 245.8. So if you go out and sample 245.8 car loans, you would get that the margin of error is $500. Obviously, you're going to round up 246. If you get 246, you're going to get something like, hypothetically here, but you're going to get something like $499, like really close to 500. Okay. 246 is stupid, Jay. I'm going to go 250. Okay, then you're going to end up with like a 490 or whatever. You with me? So you're guaranteed to be no bigger than 500. Okay, does that make sense? And always round up. Please don't round down. You look dumb rounding down. Okay? That formula is pretty sweet. Pretty easy to do, honestly. Now you're like, wait, what if I can't get a big sample size? What if I can't get a big sample? What do I do? Oh no. The t-distribution to the rescue, sir. T-distribution. Remember we talked about that in class last week? For smaller sample sizes. Okay. So again, I think the one that I always go to, and my always go-tos, is the Siberian tiger. You think it's a sperm count issue with those poor buggers in the wild. So you got to go catch them and, sample them. There's issues there, logistics, safety, money, safety, money, logistics. There's a lot of problems there, okay? From the pocketbook guy, there's a lot of money involved, logistics involved, helicopters, etc. It's expensive. I can just see the money cling. If you're the person that has to go out and do the checking, it's more about safety to you, but good luck, okay? But the t-distribution. I would like a bigger sample size. Yeah, I would too, but you can't get it. Well, what does that do for my confidence interval? Check it to nothing, actually. Check it out. It's literally the same thing, Jay. It is. The only difference is this. And by the way, whether it's a Z or a T, they perform the same thing. It's a number of standard deviations. It's a number of standard deviations. They're just a multiplier. That's all it is. Meaning that T is always going to be bigger than Z, meaning I'm going to have to go out wider with my confidence interval to be just as confident. Hey, that makes sense because the smaller the sample size, the more variability I'm going to have, obviously. If I only sample 7 or 8 things, there could be quite a bit of variability in the averages. That's true. If I sample 1,000 things, there's almost no variability in the averages. The averages are going to be almost identically the same every single time. Okay, weirdo on the other end, they cancel out, lots of stuff in the middle. The average from this size of sample of 1,000 is almost identical to this sample size of 1,000 over here. With a T, that's not true. We're going to have more variability because N is so small. We're going to have more variability here. So to be just as confident, I need a bigger target. So T is going to be bigger. Okay. In terms of how they work, they are exactly the same. Now, some books, you'll read about them. Some books will say, well, the difference, Jay, is we would actually use sigma in a Z, and we'd use T, we'd use the SX. Again, in the real world, you never know sigma, ever. So typically what we do is, like, and I say typically, I mean like all the time, we use SX, the actual standard deviation of the sample that we got, okay? But that's it. That's legitimately all there is different. So if you like, I don't know, you want a 95% confidence interval. For number of peanuts in a payday bar. I was gonna say in a Mounds, but there's exactly 2 almonds in a Mound, or not a Mounds, in an Almond Joy. It's kind of lame. Not much joy in my Almond Joys anymore. Okay, it's kind of sad. Back in my day, so you because you're poor, so you sample 15 paydays. Sure. You find that X bar is 13 and SX is 2.1. Cool. here we go. So it's going to be 13 plus or minus. I don't know what t is yet. I'm going to leave that blank. 2.1 divided by the square root of 15. Now, how do I find that t? Well, once again, oops, let's come back here. Once again, if we're doing a 95% confidence interval, whoop, still put 95 in the middle. The difference, though, is it's all about our sample size now, right? So what you're going to do is come over here, go t dot inverse. T dot inverse, and you're going to put in 0.025. Always area to the left. Degrees of freedom. Well, we said 15 was our sample size, so 14 is degrees of freedom, negative 2.14. Hey, wait a minute. Jay, that's bigger than 1.96. I said, yeah, I know. I promised you it would be. I promised you. I promised you it would be, sir. I know. I did. I wouldn't lie to you most of the time, probably. And I get 1.16 or thereabouts. It looks like 1.16. 13, and so 14.16 on the top end. Was that 11.84 on the bottom end, I guess? Huzzah! Yay, and the crowd goes wild. In terms of how we do it, they're identical. There's no difference. But again, here I am at 2.14 versus 1.96. That means this got wider, which means my margin of error got bigger, which means this interval is bigger than it would have been had it been a z. Okay? But why? Because I'm less confident. There's more variability, I'm less confident, so I have to make a bigger target to be as confident. Okay? And the last thing I want to chat about is this. The other day we did confidence interval, or hypothesis testing. And so someone very well may have said to you, blah, 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 blah. We want to know if the machine is still working. We want to know, blah, blah. Has it gotten out of adjustment? Has it changed? In other words, there's a two-tailed test. This is a big deal. A two-tailed test. Yeah, it's a huge concept. It only, what I'm going to show you, only works on a two-tailed test. It does not work on a one-tail, so please don't try it. You'll screw it up. Okay? So you go out and sample size 60, and you found that X bar was 98.7, and you found that SX was 7.2 or something. Sure. Nice. So check this out. If I did alpha equals 0.05 on a two-tail test, in reality, what am I doing? I'm putting 95 in the middle and 0.05 on the outside. Hey, wait a minute. That's literally the setup for what I'm doing here. That's right. Check it out. 98.7 plus or minus 1.96. This is a 95% confidence interval. This is interesting. What's going to happen here? I don't know. 1.96 times 7.2 divided by the squirt of 60. And I get 1.82. Oops, idiot. .52. Nice. This right here, my friends, is a 95% confidence interval for mu. Right? That's what we just found. So according to this, in theory, again, we treat it like this. It'll capture the true mean 95% of the time. Wait, but you assumed that the true mean was 100. Does that make sense? Well, yeah, because it's in here. So what would you do? You would fail to reject H0. In other words, you can use a you could use, on a two-tailed test, you could use a confidence interval to actually test it. Here's an example of one where I would reject. 0.3. If this were true, that would put us at 98.4 and 99. Uh-oh. Uh-oh, look who's not in here. 100 is no longer in there. Uh-oh. 100 is out here. Uh-oh. You mean the true mean is between here and here 95% of the time. That's right. But my assumption isn't. Uh-oh. What does that say about my assumption? My assumption is wrong. Okay? And so you can actually do it that way. Now, why would I do it that way? Okay, well, I say we, me, the kids in charge, the big kids, will often do this when they're testing between two populations. Okay? Oh, listen, I got this grant to study to see if there's a difference in like math scores or like whatever between men and women. And I did the test, and son of a gun, there was no difference. Who saw it coming? Oh, I was shocked. I was not shocked at all. Not at all. But anyways, let's say, but I got a lot of money to study it. Woohoo! Yay! But anyway, or some other ridiculous grant that's just as ridiculous. Did you know when you get monkeys stoned on cocaine, they are more violent than, say, chimpanzees? No, I didn't know. It's true. It's true. Tested it. No, whatever. Anyway, what ends up happening is, and again, I'm not going to hold you to this. I'm just showing you. This is the reason I bring it up, is because once in a while you'll see this, and it'll say something like this: the mean for, I don't know, monkeys is equal to the mean for apes or whatever. And under the null hypothesis, that's true. Or another way of saying it would be that the monkeys minus the apes would equal 0. And so what you can do is you can actually find a confidence interval for this difference. Okay? And so what you'll find is, and maybe it's this, -9, da 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 da. Hey, look what's in here. 0 is in here. These are the same thing. These are equivalent statements. Hey, look, 0 is in here. Yay! What does that tell me? It tells me I'm going to fail to reject H0, and there is no difference between those guys. Okay? And if this was from -9 to -2, uh-oh, it's not in there, so I would reject H0. That means there is a significant difference between those two. It's typically done more with a two-tailed test, or with a two-population situation, than it is with a single population. Okay? I'm not going to hold you to that. I'm just saying it can be done, but it can only be done on a two-tailed test. You cannot use that on a one-tailed test. Okay? That's confidence intervals that we're going to look at. Beyond the scope of this class, you can get into, you can find like percentages. So for instance, you want to find the margin of error, the confidence interval for a proportion. Okay. Oh, let's do that one for fun. Let's do that one for fun. And so let's say this, you want to know the percentage of people, obviously in your town, you're not going somewhere else, who like chocolate ice cream. Why? I don't know, because you run the ice cream parlor. I need to order more of it in or less of it in or whatever it is. I don't know. So you're going to sample 200 people. 30 say, no, not 30. Let's make it an easy problem. 40 say, yes, I like chocolate. I thought it'd be more. Well, this is a different town, sir. Okay, that's why we're doing these town samples. You thought you knew. You were wrong. Okay. What does that tell me? It tells me that P hat, we call that, is equal to 40 out of 200, which is 20%, by the way. Okay? Or 0.2 if it makes you happy. Wait, that means that Q hat is 0.8. What is that? Wait, P and Q, that sounds like, wait for it, binomial. Because you like chocolate or you don't like chocolate. Okay? You like chocolate or you're the opposite of liking chocolate. Whatever that makes you happy. Now, how does this work? Well, it turns out it's going to be P hat plus or minus Z, and then here's your formula, P hat Q hat over N. Okay, there's your formula. And so it's quite straightforward to bust this out. So if you do this, what am I saying? We're saying that P, the actual P, is pinched between these two values, the minus on the top end and the plus on the bottom end. So let's bust this out. So 0.2 plus or minus 1.96, 0.2, 0.8, and what did we sample? 200 people. How exciting for us. So 1.96 times the square root of 0.2 times 0.8 divided by 200. So I get about 0.055. So obviously 25.5% on the top end. That's my upper bound for P, and my lower bound, 14.5%. Yay, and the crowd goes wild. That's about all there is to it, friend. Okay, it's a slightly different formula. Done. Now, some people go, well, wait, this is very similar to on the news media when I hear them talking about so-and-so, the popularity poll, blah, blah, with a margin of error of plus or minus 3%. That's right. It's very similar. In this case, it'd be 20% of the people like chocolate ice cream with margin of error of 5.5%. Yay! That's a different way of writing it. Better, worse, nope, different. Okay? Different. That's how we do it. That's how we do it. That's how we big kids do it. Okay. Nice. Now, I would say this, that frequently, it's done such that this, by the way, p hat is the sample proportion. Frequently, it's done such that we would like this margin of error to be 3 percentage points. Okay? In other words, when we're doing these things, we like 3%. Okay, it's a big deal. Why? Because it gives me a total width of my confidence interval. My total width is 6. Yay, 6% total. Okay, that's pretty tight. It's a nice tight window. Now, that's just how I didn't get a pick it. That's just what they did. Now, you say, well, I would have gone 5. Yeah, but that would have been a margin of error of 2.5%, and that sounds weird, I think, to some people. That's a guess. No one asked me what my opinion was on it, but that's probably why. So we typically see 3%. Okay. Now, Jay, yours was 5.5% a minute ago. Yeah, it was. So if mine was 5.5%, that means that my interval, was 11% wide. That's a lot. That's not a very big. It's not a very small target. You with me? And so what we typically do in this situation is we choose an n such that the margin of error is less than, well, I typically equal to 0.03, but we should say less than or equal to. Okay, but we're going to choose n. That's what we're going to be doing. Okay, that frequently happens. And you're like, well, how does that happen? Well, the same thing it did on the other page. Same thing as on the other page. On the other page, we took this margin of error and we solve for n. And when you do that in this case, it ends up being p hat, q hat, and it becomes, so it's n over here, so z over, times z over e squared becomes that guy. Now, I know what you're thinking. How on earth am I going to know p hat and q hat if I haven't taken a sample yet, Jay? It's an excellent question. Does that make sense? I don't know p hat and q hat until I go out and take a sample. And that's going to depend on what n is, right? To some degree. Right. Well, what am I going to do? Okay, well, there's a couple ways. If you had prior knowledge, in other words, if you're doing presidential tracking polls where literally every day I go out, what do you think today? How about today? What about today? Okay, but again, what about today, Jay? What about today? Well, what about it? So if yesterday, let's say yesterday or last week or whatever, or traditionally or whatever, 30% like chocolate or whatever. All right, cool. Then I'm going to use that in my calculations here. So 0.3, and then of course Q would be I don't like chocolate, so the rest of it 1.96 because we're talking about a 95% confidence interval. And let's say again I wanted 3 percentage points. Boom, done. So if I bust this out, what you're going to see is this ends up being a fairly large number. It always does. 1.96 divided by 0.03. That happens to be 65. Square that. It's a fairly large number. 4,200 or something. And then times 0.3 times 0.7 is about 897 people. 896.7 or something. So you need to sample at least 897 people to pull this off. Cool. Nice. Awesome. But what if we have no idea about p hat? What if we don't? Okay, what if we don't? Okay. Well, remember, this is binomial. That is, the do or you don't, right? So if you have no idea, we're going to use 0.5 and 0.5. What's that going to do to me? A lot of people are not real clear on what that's going to do. So I'm going to do the same problem as last time, except I'm going to do it 0.96. I get 1,067 this time. 0.11. Why did it get wider? Because every time you take two values, P and Q, that add up to 1, and you multiply them, the biggest multiplier you will ever get is 0.5 times 0.5. Okay, prove it to yourself. Oops, 0.1, this is 0.09. It's very small. As they get closer and closer and closer to 0.5, you're going to get the biggest number, which is 0.25 for the product of them. That's going to give me the widest interval. Okay, so let's say you sampled 1,000, and let's say you sampled 1,100 people today. You with me? And when you did your sample today, let's say you sample now. So okay, you do this first. You sample 1,100 people. Nice. Let's just say we do this, okay? So then I found that P hat. Well, actually, I'll find this. J 30. Oh, not 30. Gotta do the math in your head, stupid. 300 said yes. I like chocolate or whatever out of 1,100. Okay, so let's find our confidence interval. So 300 out of 1,100. I can't do that math in my head this morning. Is about 27%. Plus or minus 1.96 and then 0.27 times 0.73 over 1,100. Okay. First things first, let's find this confidence interval, this margin of error. What do I know it's going to be? I know it's going to be less than 0.03. Oops, divided by 1,100. 0.026. Shut up. No, I won't shut up. Because I told you that's what it was going to be. Bam. Now, had I done like a 1068, I could not have rounded this a little bit. It was 0.27272727272727. You with me? So had I done with 1068, I would have had to give myself the more exact values here, here, and here, but I still would have pulled it off. Okay? Because I knew I went to 1,100, I knew I was pretty safe. Now, check this out. Tomorrow, if I was to do this, if I was going to do this tomorrow, how big an N would I need? How big would I need tomorrow to be? I wouldn't need 1,100 anymore, or in the coming days, because I have an idea of what P is now. You with me? I have an idea of it. And so my N now, what would that do? Well, it'd save me a lot of time, because I don't have to sample as many people. I could just plug it back into this formula, and then I would have a value that would make a lot more sense. 1.96 divided by 0.03 squared times 0.27 times 0.73. Now I only have to sample 841.3 people. Hey, that's quite a bit less. It is quite a bit less, 260 people less. That's quite a bit less. Hey, will that speed things up for me? Will that, I don't know, be cheaper? Yeah, obviously. So not a hard concept. It's literally plugging it in. I think the hardest concept that most people have is understanding, hey, this, I don't think it's that hard to do, honestly. You just use the formula, of course. But then the question is, hey, I want it to be 3 percentage points. Well, if I'm going to focus in on that, then I need to be able to use this formula. And so, again, if we have some background, again, presidential polling, we have that every day of the year. What about yesterday? What about today? What about today? What about today? It doesn't change drastically day to day to day. So if I knew what it was yesterday, a pretty good idea what it's going to be today, and I can use that p hat. If I have no knowledge going in, then I'm going to use 0.5 and 0.5. But after that first sample, now I have knowledge then, and I can use the newer one and take a smaller sample size. All right, talk to you later.